Okay, so let's see a running example of this algorithm. Let's see how it works, just to see that we understand what's going on. So I'm gonna ask actually Vav to guide us through the running example, just to see that we understand how this algorithm works. So do you want to start? I'll help you.
So let's go over the algorithm. The first step, we have an arbitrarily set Q values for each state and action pair. So
right, so you can see the arbitrary, I just placed it 0, 1, 2, 3, 4. Okay, but as I said previously, you can set any values there, right?
Exactly.
Okay.
So for W, there's only one action. X, Y, there's both east to west, so we have two values. And for state Z, again, just an exit action. And then we set the returns as an empty list for each state and action pair. And similarly for the policy, we keep an arbitrary policy right now, which is if you're at Y, go east, west. If you're at X, go west, and at W.
Right, so you can see this is an epsilon greedy, a soft policy, right? So we'll just say that with probability 1 minus epsilon, we'll do these actions, the one that presented in the table, and else with probability epsilon, we'll just act randomly.
All
okay?
right. Yes.
Because as we said in the previous slide, we must ensure sufficient exploration. Right.
Okay, so then we go into a loop where we start by generating an episode using this arbitrarily initialized policy. So
if you press, it will generate an episode.
Okay, so let's generate our episode.
Move a bit. That's the tau. The tau is the episode.
So yes, tau is popularly used notation to represent a sort of trajectory in RL. Here we start at state X. We go west. So if you remember, each step consists of your current state, what action you're taking, what reward you get, and what's the next state you reach. So in this case, we start at state X. We take the action, go west, get a reward of 0. Then we end up in state W, take the action exit, and get a reward of -100. Since this is a terminal state, we don't see another state. So our trajectory is X to Y. X to W.
No.
Oh, sorry. So now we are supposed to go through the steps. Yes. So now for each pair, S and A, appearing in this episode, which is X and this, exit and W would be the action and state. We see G, the return that follows the first occurrence of S and A. So the first occurrence of state X and action west. We let's calculate what the returns, what return you would get after we see take this action. So assuming, I guess in this case,
discount factor.
Yeah, here's the discount. Yeah, 0.9. Okay.
Right.
So we've taken an initial, the immediate reward is 0, and then our future discounted reward, which once you reach state W, we would have to discount it using gamma. So it would be -100 into 0.9. So our return for state X and action west would be -90.
So we set the Q value.
Yeah, so and we take that value and we append it to the returns for that state and action. And we use it to update the Q values for that state and action. Since we have only one value in this list G, our average right now for Q, X and West would just be -90. And then
right, so you can see we updated the Q values there on top, right? Okay.
Yes. So the Q values are updated, and we calculated the returns. And now we repeat this again for each and every action, and we see the Q values for each and every action. And once we're done calculating the new Q values for the states and actions in that episode, we loop through the states in that episode again to calculate to see based on the updated Q values, based on these new Q values, what would be our new policy? What would be the an improved policy, perhaps?
Right, so this follows the general policy iteration approach that we saw previously, right? So we compute the Q values, update the policy, and we do this over and over again.
Exactly. So, for instance, now in for X, our policy previously went west, but now after the update, we see that gave us a very low Q value, and now our policies, the max action in state X would now be east because it has a high Q value.
A higher, right? So it's minus 90 versus a 0.
Versus 3.
So the argument, the action argument that maximizes the Q value is right.
Yes.
Instead of left, right? So we'll
Yes.
update our policy. Press it. Oh, update.
Alright. And then, this is just update step, right?
Yeah, now we continue the process, generate another episode. Right?
So now, like I said, in state X is going to go east instead of west because that has a high Q value. But I'm not sure in this case because we do say it's randomly generated. If your epsilon is not 0, this might just be a random action also. So now we take this new trajectory and we calculate again the returns and the Q values for based on a new trajectory. As you can see, if we went from here east.
What is the new trajectory?
From X to Y, Y back to X, X to, is that W? I think we're missing the state here, but this would be W here. Yeah,
Right.
there would be a W here. So we go from X to Y, X to Y to X to W and then X.
How
So
come
now-
we took so we visited X twice,
Yes.
but took a completely different action.
That's because of the random sampling
Right,
of the
okay.
policy.
Right,
Yes.
so
So based on the
Usually
random
the-
sample, we could go either way.
okay.
And then now, if you notice here, we took an action. We went this way. That's one action. Came back, and then we get the minus 100. So this time, when we got the reward minus 100, it's much more in the future. It's going to be discounted further. So your Q values are going to be much lower. For even though you're seeing the same reward in the end, because it's highly discounted, because we saw it much later in the trajectory, you're going to see a much lower Q value for
So
that
it's
action.
actually higher. It's negative, right?
Yeah, right. Sorry.
It's much
You're
more
gonna see
discounted.
Yes, it's much more discounted.
Right.
Yes, it's you might get a higher lower Q value. I don't know, but I guess mostly higher if it's discounted, but a negative value. But here, basically, since you're seeing the same reward, but later on in the trajectory, it's going to be more discounted.
Okay, so we updated the Q values. Now we update the policy.
Yeah. So now again, we see based on the updated Q values, which is the best actions in each state. In X, it's left. In Y, it's also left. And then for Z, I guess it is.
And look, we found the optimal policy.
And yes, that's correct. That would be the optimal policy. Then,
But we don't know yet that.
Yes.
Yet, right?
so
We'll continue.
let's see. Do we have a stopping condition?
No,
here?
that's it.
No.
We have a stopping
So
condition
normally
for the
you
example.
might have some stopping condition saying if you don't see any improvement in your policy, it's converged.
Okay, but this is actually, so the pseudocode says repeat forever, so for now we won't discuss. Let's say it's a continual learning problem. Okay, thank you.
Thank you.
You did a good job.
Sorry.
Okay, moving forward. So now we can define something that is called on-policy learning, and later on we'll see algorithms that are off-policy, but this, the Monte Carlo algorithm that we just observed, is a good example of an on-policy reinforcement learning algorithm. What does that mean? So when we estimate the Q value for being at a specific state, say W, more previous example, and going right, actually, if we don't assume any noisy environment after the example that we've seen previously, we updated our estimation to be -1, which is actually the true value the true Q value for this policy, right? I'll just remind you that the true Q value is the expected return, but if there's no noise in the environment, well, it is the same as a single run, right? It will be the same, there's no noise. So Monte Carlo is very effective in converging or in learning these Q pi values, so Q values for a specific policy. However, this is different than Q star, right? In our case, Q star would be the expected sum of discounted reward from being at a specific state, in this case state W, and going right, and from that point on continuing following the optimal policy, right? What is the value for that? What is Q star W right?
It's the highest
Assume a discount factor of 1, as we saw previously.
Okay, so what value would it
What
give?
value is
Okay,
it, yeah,
so
for this example?
starting at state W,
Mm-hmm.
we would see plus 10? We're going to the
Plus
trend?
10, yeah.
Yeah.
If you have a discount factor of 1 and you do assume no battery drain, or anything like that, no living reward, then your optimal policy will continue going right and get the plus 10 reward, right? So Q star is plus 10, however, we didn't notice that, okay? Or it was difficult for us to learn that. We were only able to learn, for now, the Q values for the specific policy that we are following. But once eventually we would like to learn Q star values because they imply the optimal policy. A step before that would be to be able or to try to learn the Q value for any policy that is different than the policy that we are using to interact with the environment. We'll call that B because normally this is denoted the behavior policy, right? The policy that we use to behave in the environment, and that might differ than some policy pi for which we would like to learn. Ideally, right, eventually we would like to learn for pi star, but I'm asking a bigger question here, which would be, yeah, can we learn Q pi for any pi that is different than our behavior policy? And this seems to be a difficult task, specifically if you're using Monte Carlo approach, right? Because, well, the Q values or the set of rewards that we observe belong to or depend on the specific behavior policy that we're using in order to interact with the environment. So, the observations drawn from some policy pi are very useful in evaluating the Q values for that policy. But once the policy is changed, or we're trying to learn the Q value for a different policy, these observations will become irrelevant. Or they become irrelevant in a straightforward way, but we might use some tricks, and we'll discuss them in a second. And this is not what we call sample efficient, right? Because we interact with the environment and we use these interactions in order to learn something about, well, hopefully about the optimal policy, towards the optimal policy. But if we use policy iteration, that is, we use a policy, we have some observation, we use those observations to update Q values and then update our policy. But then, once we update the policy, we say that, well, all of the observations that we previously saw before updating our policy become completely irrelevant. It's not sample efficient because, well, as we know from our everyday life, even if we slightly change our policy, specifically if we change our behavior ever so slightly, our previous experience might still be relevant to some extent, right? And the question is, how can we use such previous samples, such previous experience, in order to help us converge towards the optimal policy, even though we change the policy over? And so this leads us to the not necessarily a requirement, but some something that we desire. We desire to perform off-policy learning, to be able to learn regarding some target policy by following a completely different policy, or to use samples that are drawn from a completely different policy regarding some target policy that we really care about. Okay, specifically later on, the motivation here is, of course, specifically we would like to learn Q of pi star, because then it will imply pi star. But for the sake of this discussion, let's just assume that our target policy is anything that differs from our current behavior. Eventually, we strive for full utilization of previous experience, and off-policy learning allows us to do that. Specifically, it allows us to optimize the target policy while following another behavior policy. The pros of doing that, of course, is that it's much more sample efficient. The cons, as we will see soon, is that it provides us with high variance estimations regarding the target policy. High variance meaning that it will be very noisy, and I'll show an example soon. So some conditions that are required in order to allow us to perform off-policy learning. That is, when our objective is to use some episodes, some samples drawn from some behavioral policy B to estimate some target policy, a different target policy pi, is as follows. So for off-policy learning, we must assume coverage. That is, that any state and action that has non-zero probability from being sampled by our target policy pi must also have a non-zero probability of being visited by our behavioral policy B. Okay, that is, we must be able to observe all of the reachable state and action pairs, reachable by our target policy, in our behavioral policy, in order to learn something about them. And that makes sense, right? So hopefully it does. That is, we won't be able to learn anything about state and action pairs that, well, we don't sample. Okay, so if this is true, then by running our behavioral policy repeatedly, we will eventually discover all possible trajectories for pi, probably not with the same probability, right? So it might be the case that some trajectories might be visited often if we use pi, and not so often while we use b, but that's okay. So if coverage is violated for some state and action pair, then no inference is possible regarding that state action pair. Okay, so I said that, right? And hopefully this is obvious. Okay. Second.